Hello everyone, today we're going to be talking about modeling with exponential and logarithmic functions. So first thing that we can do is classify data. And so we see that most real-world data form a pattern that can be modeled by one of the functions we have learned. And so we can look at finite differences or common ratios to determine what type of function best fits a data set. And so for today we're going to be focusing on these four different types of families of functions. First, we see linear, and remember that rule or the parent function is f of x is equal to x, and that creates a straight line. And the thing we see here with its data, anything that follows a linear pattern, is that it has constant first differences, I'll highlight that, between y values for evenly spaced x values. For a quadratic, on the other hand, its rule is f of x is equal to x squared, and remember that creates this parabola shape. And it's pretty similar to linear, except here we see it has constant second differences between y values for evenly spaced x values. And we'll see an example of that here in a second. And then we have our exponential and logarithmic, which is what we've been focusing on this unit. Exponential, its rule is f of x is equal to b to the x. And here we see constant ratios between y values for evenly spaced x values. So that means it's being multiplied by the same thing each time. And then for logarithmic, that one is f of x is equal to natural log of x. We see this graph. And it also has constant ratios, but now it's between x values for evenly spaced y values. So all these other ones, we were looking at the pattern in the y values for evenly spaced x values. For logarithms, we see the flip of that. Their constant ratio is happening between the x values for evenly spaced y values. So let's get some practice of looking at data sets and determining what type of function is represented. So I see for number 1, I have my x's are going up by 1 each time, so those are evenly spaced. I can even make a note of that. That's saying, okay, my x is evenly spaced. And then looking at my y values, I'm looking for a pattern. So I can first look to see, okay, am I adding or subtracting the same thing each time? Looking here, I see I go up by 0.5, then 1, then 2, then 4, then 8, and so on. It's not that. However, looking at this, I notice I am multiplying by something by the same thing each time. I see that I'm multiplying by 2 each time. So that means I have a constant ratio of 2 here. Between y values for evenly spaced x values. And so because I have a constant ratio between y values for evenly spaced x values, that makes this one exponential. So exponential is when y is being multiplied by some number every time. Okay, let's look at number 2. Number 2, I see my x values go from -2, 0, 2, 4, 6, 8, 10. So I'd say I'm going up this by the same amount each time. So my x values are evenly spaced. Now looking at my y's, I see I go from 2 to 0 to 2 to 8 and so on. So looking at that, I see I'm not multiplying by the same number each time. So I'm going to be looking at my differences here. To get from 2 to 0, I subtract 2. To get from 0 to 2, I add 2. 2 to 6, 2 to 8, I add 6. 8 to 18, I add 10. 18 to 32, I'm going to add 14. And 32 to 50, I see that I add 18. So I see my first differences, they are not the same. They're all different numbers. So now I'm going to look at the second difference. To get from -2 to 2, I add 4. 2 to 6, I add 4. Add 4. Add 4. and add 4. So I see that my second differences are the same. So I can say these are, let's do purple, second, I can say constant, second difference, between y values. And so since I have a constant second difference between y values, that means that this one is quadratic. Okay, number 3, I see on my x values that these are evenly spaced. I go 0, 10, 20, and it's going up by 10 each time. Now I'm going to look at my y values. And so looking at this, I see they're all pretty close together, and I see to get from each number, I am subtracting 3 each time. And so here I have a constant first difference between y values. And so here, since I have a constant first difference between y values for evenly spaced x values, this one is linear. And now for this last one, I see that my x values are not evenly spaced this time like the other ones. However, my y values are. I see I am going up by 4 each time. So this is evenly spaced. But then from my top here, I see to get from 3 to 1.5, 0.75, 0.375, I'm definitely not subtracting the same number each time, but I am multiplying by 1/2 each time. Or in other words, I'm dividing by 2. And so here I have a constant ratio between y values. And so, no, not y values, sorry, x values this time. And so this time, since I have a constant ratio between x values for evenly spaced y values, that is going to make this data set logarithmic.